So I'm very glad to introduce the talk by Colin Crowley. Colin, please.
Okay, so thank you very much. And thank you for inviting me to speak here today. I was very excited to discover that the sorts of things that, me and, the other people here are thinking about are connected to this community and this literature. So I am very excited to meet you all and to talk to you. As might become clear when I begin talking, I'm from a very different background and, a different field. So my hope today is that I can introduce this field a little bit and in a clear way, hopefully, and to tell you a little bit about where is the connection to equivariant completions of affine spaces. And yeah, so I don't have a good idea of which parts of what I say will be natural to you and which parts will look strange. So at any point, if you'd like more explanation about something or if something was unclear, please do interrupt me and ask. Also, if I talk too fast or if I'm hard to understand, also please feel free to interrupt me. Okay, cool. And can everybody see my screen?
Yes, we do.
Awesome.
Yes.
Okay, so the slides that I'm gonna show you are, I have a link to them here, so you can download them and flip through them if you like. I've tried to include references for everything I'm gonna say, so if you'd like to read more, you can. And the outline of what I'm gonna talk about today is, I'm gonna start by just introducing Matroid theory very quickly without going into too many details, but giving you a sense of the world that I come from. And then how do these equivariant completions enter the story? And so the two groups that I will be talking about equivariant completions of are the additive and the multiplicative group of complex numbers mostly. Yeah, for concreteness, I'll be over the complex numbers. It works for algebraically closed of characteristic 0 and with slight modification for any algebraically closed field. And the main result that I'm going to talk about is a sort of correspondence theorem. And this is between equivariant completions of products of the additive group such that several quite strong conditions hold. So this ... there is a lot that is being suppressed at the moment. But compactifications like this will be in one-to-one correspondence with hyperplane arrangements. And it's tempting to compare this to this correspondence between toric varieties. These are equivariant completions of the torus, Gm to the D, and polyhedral fans. And there are some similarities and some differences between these two correspondences. And I'll compare them and explain what are these similarities and what are these differences. Okay, so first, let me tell you about my background. So this is Matroid theory. And actually, I should ask, are there any questions about this before we get going? Okay, very good. So Matroid theory. And another word for a matroid is a combinatorial geometry. So you'll see both words in the literature. And the goal of Matroid theory, as it was put by kind of Giancarlo Rota, who is one of the early popularizers of matroids, the goal is to find a natural setting, to generalize to a natural setting, the theory of arithmetic invariance of a finite set of points in projective space. And this is rather old language, calling these arithmetic invariance of finite sets of points. But so what do I mean by this? I've drawn two pictures here of finite collections of points. These are both in P2. So the one on the left, this could be P2 over C, let's say, or any field of characteristic 0. I could have these points and they define among them some lines. So I've drawn 4 lines here. These are the lines that where kind of points on these lines are not in general position. And of course, between any 2 of these points, they also define a line like this. And one wants to count these lines and do combinatorics with this arrangement. You could also, on the right hand, I have this famous Fano plane. So this is the arrangement of all F2 points in P2 defined over this F2, the field of order 2. And if you zoom in, you can see this picture that I got from the internet. It has the coordinates. So these are all of the points, coordinates 0, 1 in the projective plane. And since it's characteristic 2, it's possible for these 3 points, which don't lie on a line in characteristic 0, they can lie on a line in characteristic 2. Okay, so this is roughly what a matroid will look like. And we're interested in these sorts of questions. When do 3 points lie on a line? When do 4 points lie on a plane? How many planes are there? These sorts of counting problems. And really to get a natural setting, we wish to forget the coordinates. So it doesn't matter exactly what the coordinates of this point are. All that matters is the linear relationships between these points. And so this leads to the definition of a matroid. So this was introduced in 1935 by Whitney. And here's the definition. So it's a pair, E and I. So E is a finite set. This is supposed to be the points. This is a set of points, together with the data of which points are linearly independent. So I is a subset of the power set of E, and any set in there I declare as independent. And this data should satisfy a few axioms. So the first is that the empty set is independent. This is okay. Any subset of an independent set is independent. And the third axiom is more interesting. It says that if I have 2 sets of points, I and j, and one of them is bigger than the other one, let's say I is smaller than j, then there must exist some extra element in j, such that if I add this extra element to the first one, I add it to I, the resulting set is still independent. And so this is a mouthful, so I've drawn a picture of what's going on here. So here, try to get both at the same time. So in red, I've circled the set of points I, and in blue, I've circled a set of points j. And j is bigger than I. And there is a point, this one right here, which is independent with respect to the 2 points in I. However, not every point in j will work. For instance, this point, there is a linear dependence between this point and I. Okay, so this axiom is capturing some property of point arrangements.
May I ask a question, please?
Yes, please.
So if we say that any subset is independent, then we can care about maximal independent subsets only and forget everything else.
Yes, that's exactly right.
But, is it true? It seems to me that the third property says that maximal independent subsets are of same size.
Yeah, that's exactly right.
Okay.
Yeah, so a maximal independent subset is called a basis, and the size of a basis is called the rank of a matroid.
Thank you.
I also have a question. We mean geometrically that independent set is the set of points that doesn't lie on some plane or line or something like this.
Yeah, so I think the way the numbers work is it's an independent set of size 3 is 3 points that don't lie on a line, an independent set of size 4, they don't lie on a plane. Yeah, that's right. Yeah, other questions? Okay, very good. So that's the definition. And now some terminology. So as I've showed you before, given point arrangements, they do satisfy these axioms. And so any matroid that is coming from an arrangement of points, I'm going to call realizable. And what the interesting thing is that Whitney was, he thought that every such arrangement must come from points in projective space, but this is not true. So there are some matroids, they satisfy the axioms. However, they don't come from points in projective space over any field. And I've drawn an example. I mean, I have a picture of an example from Wikipedia of such a thing. So this is called the Vamos matroid. And what this diagram means is, so these 4 points are not independent because they lie on this blue plane that are pictured here. So each one of these blue planes corresponds to a dependence relation among a set of 4 points. But for instance, these 4 points, in this matroid, these 4 points are required to be independent because there's no plane containing them. And likewise, these 4 points, the 2 top and the 2 bottom, there's no plane containing these 4 points. And these 4 points, for instance, there's no plane containing them. And so if you stare at this picture for a long time, you can convince yourself that at least in, P3 for characteristic 0, you can't embed this diagram so that all of these independence relations are preserved. There will have to be an extra dependence that isn't pictured here. And it turns out that you can't even do this in positive characteristic. In no projective space can this embed and preserve all of the dependence relations. Okay.
So am I right that this is a very bad news for Matroid theory? So this attempt to formalize, to characterize axiomatically dependent set was unsatisfactory somehow, right?
Yeah, that's right. And it was unsuccessful in a very interesting way, as I'm going to talk about in a second, I think. There's a very fun paper that has the title, "The Missing Axiom of Matroid Theory is Lost Forever." So, Whitney thought that these axioms should describe point arrangements in projective space exactly. And he was disappointed when he realized he thought maybe an axiom is missing from the definition. And there are some sort of computability, I think well, I'm not so familiar with the details, but there are some statements to the effect that no such axiom is possible in a reasonable way. You always miss something. Yeah. Okay, so these are matroids, and now I want to talk about some recent progress in matroid theory. So this past year, Junha received a Fields Medal for his work on developing Hodge theory for matroids. And let me say a little bit about what this is without going into too much. So given a matroid, you can define a theory of cohomology in actually 3 different ways at the moment. So here are these references, 1, 4, and 3. In each of these references, they define a notion of cohomology for a matroid. And what's really shocking is that this cohomology behaves like the cohomology of a projective variety. And what I mean when I say this is that three theorems from Hodge theory hold. So first of all, there's Poincare duality, and then the Hard-Lefschetz theorem, and the Hodge-Riemann relations.
Sorry, the 3 cohomologies give the same cohomology? So the 3 definitions, they give the same result? Or
they give different. Yeah.
They're different cohomologies, but they all satisfy?
That's
projective?
right.
Oh.
Mm-hmm. Yeah. And these 3, these are often called the Kähler package together. Kähler. Right, so even if this was true once, that would be impressive. But the fact that it's true for 3 different cohomology theories is very, very shocking, I think. And if this comes actually from a point arrangement over the complex numbers, over any field really, but for classical Hodge theory, it's the complex numbers, then one can construct from the data of this point arrangement an algebraic variety. So these 3 different theories come from 3 different constructions. Yeah, I'll tell you about one of the constructions, but one constructs a variety, and the Hodge theory of this variety turns out to only depend on the combinatorics of the matroid. And that's over a field. And what's really interesting is that it's true even for matroids that don't arise over a field. So for a general non-realizable matroid, this Hodge theory is still true, but it follows from the matroid axioms. There is no algebraic geometry involved in the proof. Okay, so this is a very brief introduction to this area. Maybe any questions that you'll have at the moment? Yeah, I have one more slide on this, and then. Okay, so there are many parts to this story, and I want to tell you about just one part. So this is the work on the so-called top-heavy conjecture. So what does it say? First, some notation. So suppose I have several points in projective space, PD. Let's assume they're not all contained in a hyperplane, so they actually span projective space. The number of points, lines, planes that these define, I'll denote this by this vector, W's. So just to do an example, suppose I just have 4 general points in the plane. Then these 4 points define 6 lines, right? Any combination. So here, W0, I suppose, is 4. W1 is 6. Okay, so here are these numerical invariants. And a theorem in 2017 by Junha and Botong Wang is that in this setup, given several points, not all contained in a hyperplane, there exist inequalities among these invariants. So the first inequality says that the number of points is at most the number of hyperplanes that they define. And this inequality is more classical. This was known to Erdős and De Bruyn. They give the history of this problem in their paper in 10. And the rest of the inequalities that, W1 is at most WD minus 2. So this is the number of planes defined is at most the number of codimension 2 subspaces, and so on and so forth. All of these inequalities were new at the time. And this was conjectured that all these inequalities should hold in 1975 by Dowling and Wilson, who showed a similar set of inequalities that are slightly weaker. Okay. And okay, so this is a problem. It's a very elementary to state problem. And what's very surprising is that the proof is very geometric. So the idea, okay. So here's the idea of this proof. I wish I had time to say more about it. I'm not going to say that much. So the idea is to find magically some singular projective variety Y that has the property that the Betti numbers, this H is the singular cohomology. The Betti numbers of this Y are exactly these numerical invariants that we were trying to count. And the second property is that the singular cohomology of Y injects into its intersection cohomology. So yeah, intersection cohomology is this theory of cohomology that works very well for singular projective varieties, in case you're not familiar. And there's always a map between the two. And for this to work, one needs to know that this map is injective. And you can prove this by knowing whatever this magical Y is. And once one knows this, it follows from this Hard-Lefschetz theorem, right? This theorem from the Kähler package, that actually these inequalities will hold. And okay, so this is very roughly the idea of their proof. And this proves the conjecture for realizable matroids, ones that come from point arrangements. And again, surprisingly, all of this theory, right, this intersection cohomology and the Kähler package for it, can be generalized to arbitrary matroids. So one proves the Kähler package for intersection cohomology, in this case, from the matroid axioms. And that's this paper 4 that I'm citing here. So this is some notion of singular Hodge theory for matroids. This was in 2020 by He and Wang, and also 3 other authors, Tom Braden, Nick Proudfoot, and Jacob Modern. Okay, so this, Matroid Hodge theory implies that actually the conjecture is true for all matroids, even the ones that are not realizable. Okay, so this is a story. Botong Wang is my advisor. And when he gave me a problem, he told me to study the structure of Y as an equivariant completion. So where this story makes contact is that this Y that was so crucial to this proof, and that it's the model for one of the cohomology theories of a matroid. It is an equivariant completion of GA to the D. And so, at the time when I started thinking about this, I really knew nothing about equivariant completions of GA to the D. And yeah, the goal was just to see, like, of the many equivariant completions that they are, which ones are these? Which properties characterize these examples that showed up in this proof? Okay, so this is where it makes contact. Questions at this point?
So how did they find this Y?
Yeah, how did they find this Y? So there's one of the other cohomology theories I mentioned. This is called the Chow ring of a matroid in the literature. This comes from a different variety, the wonderful model. And there's a certain sequence of blowups and blowdowns that get you from the wonderful model to this Y. And so, as I understand, they were thinking about how it was related to this other variety. And they realized that if you kind of transform it in this way, you get something else, and that happens to have the right cohomology, something like this. And this Y, as I'll point out, it was written down in a paper in 2016 for a different reason. And when they realized this is what they needed, they found this paper, and yeah. So 2016 is when this Y was defined, and in 2017, these 2 authors realized that it was what they needed.
Thanks.
Yeah. Okay. Okay. So this is the end of the story of where I came from, and now I want to start over, basically, and talk about this Y. This will be sort of the subject for the rest of the talk. So first, let me give some definitions that you may all already know, but I will give them anyway. So the setting is G, a commutative linear algebraic group. There are only several examples of such things. They are products of the additive group and the multiplicative group. And an equivariant completion of such a thing is a complete variety, X, that has G inside of it as a dense open set, and an action of G, which extends the multiplication, the group multiplication. And if I remove the word complete, then I'll call this an equivariant partial compactification. Okay, so these are the definitions, and sort of a very nice example is toric varieties. These are precisely normal, one often includes that, equivariant partial completions of just copies of the multiplicative group, of just the torus. And the very beautiful theory of toric varieties tells you that while they're defined as equivariant completions, they're really classified by polyhedral fans. And there is this very nice dictionary between these compactifications on one hand and these rigid polyhedral objects. Very beautiful, very nice dictionary. And there are many examples of equivariant compactifications or equivariant completions of GA to the D. There are many, many more, I guess, than toric varieties. This is my sense. And this is, something that I don't know so much about the general theory. This is part of why I'm excited to talk to you all. And from my perspective, there's a very small subset of these examples that are these Matroid Schubert varieties. So this was the Y. So we have some very small class of these, and we're interested in learning how it relates to the general theory. Yeah. And kind of in order to, justify to you that this is a small subset, all of the interesting ones are singular. So for instance, the only smooth example of a Matroid Schubert variety is P1 to the n. It's a power of P1s. So all of the others, all of the interesting ones have singularities. So this is a very small and, a small class, I suppose. This is all I want to say.
So wait,
Okay.
but is it really small? So among toric varieties, the singulars are most of them.
This is true. Yeah. So
I'm not so sure
compared
if
with
in this case, being singular equals to being small.
Yeah, so this is, compared with toric varieties. So there are exactly as many as there are hyperplane arrangements. And so for me, there are many interesting hyperplane arrangements. But I guess when I say small, I just meant that, like, as I've read all of your papers, and there are not so many examples that I found of singular situations. So maybe small is a bad word, like orthogonal might be a better word. Yeah, I don't want to give the sense that basically every equivariant completion is one of these, although, maybe you all know more and you wouldn't have the sense anyway.
Thanks.
Yeah. Yep. So yeah, these will show up in the correspondence, as I said. There are exactly as many of these Ys as there are hyperplane arrangements. Okay, so let me give you the definition. It's not a very complicated definition. Here's some notation. So I'll be over the complex numbers. Y will be the additive group C to the D. And then I'll have n linear forms on my vector space. I'll denote by H's the kernels of these forms. And A, math script A, will be the hyperplane arrangement that they define. And I'm going to assume that the intersection of all these hyperplanes is 0. It's not such an important assumption, but it's convenient. And then finally, let me note that there is a matroid here. So I've chosen to use a hyperplane arrangement instead of a point arrangement. But this is, of course, by projective duality, they are equivalent. And for this construction, it will be more convenient to use hyperplanes. And okay, so here's the notation, and now here is the definition. This was, as I mentioned before, given by Federico Ardila and Adam Booker in 2016. And here it is. It's YA is how I will denote it. And it's the closure of V, the vector space, in P1 to the n, where I have to say how it embeds into P1 to the n. And the embedding is, first you embed into C to the n using these linear forms. It will be an embedding because this intersection is 0. And then each copy of C sits inside P1, the standard Riemann sphere. And so Cn sits in P1 to the n. And then I embed V in here and I take the closure. So this is the definition. And let me remark a little bit about the name. So you may ask, what does this have to do with Schubert varieties? And directly, so the authors of 4, so this is a paper that proves one of these cohomology theories, the one that goes with Y. They like to call this a Matroid Schubert variety because another part of this story is that there is a Kasdan-Lustig theory for matroids. And in this Kasdan-Lustig theory for matroids, Y plays the role that a Schubert variety would play in Kasdan-Lustig theory. And so because of this other analogy that they consider, they like this so much that they call this a Matroid Schubert variety. However, it's a thematic comparison. There's no, at the moment anyway, there's no direct connection between these and Schubert varieties. So yes, so this is the name. This is where it comes from. And yeah, this is what it is. Questions at this point that people have?
At least emotionally, this is somehow unnatural to consider Cn as an open subset inside of the product of lines. Usually this is an open subset in Pn. And in this case, some efforts are needed to imagine this. But yeah, formally it's clear.
Yeah, exactly. And the sort of intuition that I can offer for why this is what you want to do in this case is that if I took the closure of a vector space in Pn, it would be isomorphic. Like it doesn't matter which vector space I take the closure of. I always see a projective space. And from the perspective of matroids, this is bad because all of these independence relations live in sort of the coordinates of this Cn. So, from my perspective, something that's highly coordinate dependent is a good thing. Yeah.
I also have a question. You write y subscript a. So y depends on a, but does it depend? Well, we can have different a's, different linear functions that give the same embedding, the same subset in Cn, and the same variety. So is it usual that different a's give rise to the same Schubert variety or not?
No. So non-isomorphic hyperplane arrangements give you non-isomorphic Schubert varieties.
Okay, thank you.
Yeah. However, the choice of linear forms doesn't matter. So if I scale the linear forms, say, this doesn't change anything.
Now I see, because it depends not on the linear form, but only on the hyperplane. Because if you multiply linear form by a scalar, it doesn't change your embedding because this is in P1, right? So
I think it'll move the vector space by an action of the coordinate torus on P1.
Okay.
Yeah. Okay. So now where is the equivariant structure here? So I'll write P1 as C and infinity in the standard way. And then of course, C inside of P1, this is an equivariant completion where, the action is really the only thing it could be. So I add complex numbers in the usual way. And given a complex number, I say it acts on infinity by just fixing infinity. And now taking products of this example, I can see that Cn inside of P1 to the n is also an equivariant completion. And finally, V, we embedded it into Cn, and it's a subgroup. So its action on itself preserves itself. And therefore, the closure, Ya, is also preserved under this action of V. So when you try to write down these varieties, it's quite simple. Like this Y is a set of vectors where the entries are complex number or infinity. And to act by an element of V, it's the very simple rule where you add coordinate Ys and two complex numbers add in the usual way, and any complex number plus infinity, it's infinity. It's quite satisfying to write out and very simple. Okay, so this is the definition and the equivariant structure. But one thing that's maybe not clear yet is what is happening at the boundary, because this is not such a usual thing to do. And I've told you that most of these ones are singular. So something complicated is happening at the boundary. You're picking up some singularities. So let me try to give you a description which will show you what is happening at the boundary. So the description is that you can transform the projective space into Ya using blowups and blowdowns. This is in this paper of Ha and Wang So here's the diagram. Let me explain it. So I embedded V into Cn, and so I can take the projective closure. This will be V inside V closure, a projective space inside Pn. And now Pn, this is birationally equivalent to P1 to the n, of course. And I can resolve this equivalence using toric blowups and blowdowns. So this, here I'm blowing up Pn to some toric variety, x sub sigma, and I can blow up P1 to the n to the same toric variety. This is some statement, we know the fan of Pn and P1 to the n. I find a sequence of subdivisions like this. And then once I've transformed Pn into P1 to the n, when I take the closure in Pn, it will transform via the proper transform, right? Proper transform up into this toric variety and then push it down. It will transform into the closure in P1 to the n, right? So this birational equivalence is resolved by looking at how it intersects the centers of the blowups of these toric blowups. Okay, and maybe a concrete example of this. So suppose I have V embedded into C3 in general position, and V has dimension 2. So to get this YA, I start with P2, and I blow up 3 points at infinity along the line at P2, and then I blow down the line at infinity. And okay, so this is the left triangle of this diagram above. P2, blow up P1, P2, P3 on the boundary, and then contract the line at infinity to get YA. And I've drawn a little cartoon of what this may look like. So here I have P2. It consists of an affine space, C2, and then this boundary line at infinity. I've blown up my 3 points. These create 3 exceptional divisors that live in the boundary of C2. And by the way, this is an equivariant compactification because the points I blew up were fixed by C2. Okay, so I now have these 3 exceptional divisors on the boundary, and then I contract this line. And when I do so, the 3 exceptional divisors will now intersect at 1 point. So this YA in this situation, it consists of C2, and on the boundary, I see 3 lines intersecting at 1 point. This point right here will be singular. And the way you can see this when you calculate is that these 3 lines, the tangent vectors are independent. And so the dimension of the tangent space at this point is 3, even though it's just a surface. So that's where the singularity is coming from. Okay, so hopefully this helps you imagine what is going on. And okay, so now let me tell you about this correspondence. So this is the main result. And again, let me remind you of the question. There's this very interesting class of equivariant completions, these YA, Matroid Schubert varieties. And we're very interested in knowing how broad is this class, right? Given any equivariant completion, can you tell whether or not it arose in this way? And this is the theorem. So here it is. An equivariant completion of YA is isomorphic to a Matroid Schubert variety, is one of these Ys, if and only if a few conditions are met. So the first one is that it has to be normal as a variety. That's okay. I'm going to ask that it has finitely many orbits under the additive group. And this already is quite restrictive because even projective space in the usual, what I call the usual action of the additive group on projective space, there's infinitely many orbits at the boundary, unless it's P1. So even projective space besides P1 does not satisfy this. there is an action. Okay, I'll say something else in a second. So that's the second condition. And the third is even more restrictive. So I guess the third and the second is more restrictive than the second. I don't have a good sense of how restrictive the third is in general, but I'm going to ask that every orbit can be reached by going straight in one direction in the affine chart. So given any vector v and v, I can scale it by complex numbers and take the limit as t goes to infinity. And that will be some, it won't converge in the vector space, but it converges in the boundary since y is complete. And that will lie in some orbit, some boundary orbit. I ask that every orbit can be reached in this way. And okay, so first the corollary. So if these three conditions are met, then it's a Matroid Schubert variety. And as I've discussed, Matroid Schubert varieties, they're in one-to-one correspondence with hyperplane arrangements. So when you put these two together, it means that if you have some completion satisfying these properties, it comes from a hyperplane arrangement, right? It corresponds to a hyperplane arrangement that determines all of its structure. And the remark, so I want to tell you where these conditions came from. How did we guess them? It's because, I was thinking about toric varieties. So normal toric, so toric varieties are normal. That's, usually one defines them to be normal. And they all have finitely many orbits automatically. So it's not part of the definition of a toric variety, but it does follow that every toric variety has finitely many orbits. And when you construct the fan of a toric variety, there's one-parameter subgroups of the torus play an important role. And in particular, each orbit has this distinguished point that can be reached by a limit. T goes to 0 of t to the v, where v is some integer vector, and t to the v is like, t to the v1, t to the v2, so on. Okay, so these are the one-dimensional subgroups of the torus. One-dimensional subgroups of a vector group are just spans of vectors. So this is how I see this condition as an additive analog of this sort of one-parameter subgroup property of toric varieties. Okay.
May I ask you a question?
Mm-hmm.
As to me, all three conditions in your theorem are very unexpected. But I would like to ask about only the first one. Mm-hmm. Your Matroid Schubert variety is defined as a closure of something.
Yeah, that's right.
Usually, if you take a closure of something in the vector space or in projective vector space, this is usually non-normal. Yeah. What is the reason why it is normal here? Can it be explained somehow?
Great question. So I know two explanations. One is where you just cite a general theorem, and one is more sort of involved. But so there's this paper of Briand that I can send you a citation, or there's this paper of Briand which says that if I have a flag variety, so p1 to the n is a flag variety, and I have some subvariety of this flag variety, so this ya is a subvariety, and it has the property that its Chow class can be written as a linear combination of Schubert varieties such that all of the coefficients are 1. So he calls this a multiplicity-free subvariety. If this is the case, then magically it is normal in Cohen-Macaulay. And this is sort of a degeneration argument. So you could degenerate ya into a union of Schubert varieties in p1 to the n. They will just be smaller products of p1 to the n. And then you use the fact that this special fiber is going to be normal in Cohen-Macaulay by properties of Schubert varieties. And then you can deduce it for ya. So this is some general result that we can cite. But you can also, Ardila and Booker, in a more concrete way, prove that it's Cohen-Macaulay, this ya. And by understanding the singular locus, you can check that it's smooth in codimension 1. And so, for instance, Cohen-Macaulay plus smooth in codimension 1 also implies normal.
So how do you get Cohen-Macaulay from your theorem? So 2 implies Cohen-Macaulay?
So
you said it comes from a bigger theorem, so it should be included in this.
Comes from a
So
bigger.
these three should imply Cohen-Macaulay then, no?
Yeah, that's right. You're right. These three imply Cohen-Macaulay.
I don't see how.
Yeah. Yeah. I don't have a good intuitive explanation for why
Okay,
this is
thanks.
true.
I will think about it.
Okay. Yeah. So this is the result. Yeah. Let me say some more about it. So this slide is maybe not so necessary for you all. When I talk to people who study matroids, they like to see these examples. So let me do some examples where these conditions are not true. So of course, there's the usual projective closure, C inside of P2. And as I mentioned before, this is going to have infinitely many orbits. However, it is true that every point in P2 can be reached by the limit of a vector, V. So one condition succeeds, the other fails. And there's also this other action of C2 on P2, which, as I understand, is due to Hasid and Schinkel, where C2 acts on P2 via this sort of exponential action. So given a vector xy, I write down this matrix. This defines an action with a dense orbit, and we can identify C2 with this dense orbit. And under this compactification, there are 3 orbits, and one of them cannot be reached by this line. So the one-dimensional orbit in P2, so this is like the boundary line minus a point. To reach this orbit, you have to move parabolically. Yeah, so this is an example that I'm sure you all know. For me, this was quite surprising that this exists. And okay, maybe let me spend the last few minutes comparing this correspondence to toric varieties. Yeah, so here's my comparison, and then that will probably be it. So first I need to give a definition. So suppose I have several hyperplanes, like this perhaps. These are linear hyperplanes, so not affine. A flat of this arrangement is simply a linear subspace that I can get by intersecting hyperplanes. So there are 5 flats in this example, flats. They are C2, so empty intersection of hyperplanes, I say, is just C2. This example is in C2. There are the single hyperplanes themselves, and there is the 0 subspace, right? So really, this hyperplane arrangement, it stratifies C2, and the flats are just the strata. Okay, so this is what a flat is. Okay, now let me make the comparison. So first of all, let me recall some notation about toric varieties. So T for me is going to be the torus, GM to the D. I'm going to have a collection of characters, the U's. The character lattice I'm going to write as M. And I'm going to assume that these characters span a cone. And what I mean by this is that if I take the semigroup they span in this lattice, it's of the form, sigma dual cap n for some cone sigma dual. And I'm thinking of sigma in the standard way as a cone in n in the dual lattice. And then the toric variety that this data defines is nothing but the closed image of this torus in a bigger torus, GM to the n. And then I put this bigger torus into A1 to the n. So, and where A1 is GM union 0. So this is A1. So this is AN, and sort of this closure of a subtorus in AN is a toric variety. So that's how one can construct a toric variety associated to a cone. And the orbits of this toric variety correspond to the faces of the cone. And finally, sort of a trivial observation, which will be important for comparison, is that this variety, this U sigma, is affine because GM union 0 is A1. That was affine. Okay, that was a trivial observation. Let's continue. So in this other case, I have this Matroid Schubert variety. There I have this, this additive group, V. And these L's from before, these linear forms, these live in the dual vector space, which is nothing other than the Homs from V into GA, just as characters were Homs from T into GM. And I assume these L's are a spanning set. That's this condition that the hyperplanes all intersect at 0. This YA was defined by taking the closed image of first I embed the additive group V into GA to the N. And then each GA, I can add the infinity point to get P1. So here I'm taking the closure of V and P1 to the N to get YA. And one of the orbits of YA, they correspond to flats of the hyperplane arrangement. These are these strata that I talked about in the previous slide. And the correspondence works very similarly to how it works in toric varieties, which I'll talk about on the next slide. And then here's sort of this odd feature, which is that this Y, it ended up being projective, and this was because GA union infinity was projective. It's P1. So I think many parts of, I think about this analogy as many of the formulas are the same, but there's this very strange thing that happens where affine toric varieties are sort of like projective, are like Matroid Schubert varieties, they're like affine toric varieties, which is strange to me because one is affine and the other is projective. But in any case, here are the formulas. And I have one more comparison to make before I end. So, okay, so here's comparison 2. So again, let's do toric varieties. Let's have a torus. And this time I want a complete toric variety. Right, and now what I'm trying to do here is recover the fan from the toric variety. I want to go the other way. And to do this, I consider the opposite lattice, N. This is the lattice of one-parameter subgroups or co-characters. And I can define an equivalence relation on this lattice by I say that two one-parameter subgroups, lambda 1, lambda 2, are equivalent if the limit as t goes to 0 for each one is the same. So this limit will lie somewhere in the boundary of this toric variety. But if it's the same boundary point for two one-parameter subgroups, I say they're equivalent. And these equivalence classes cut out the cones of the fan. So in the familiar P2, one has a fan like this. And if I choose two lattice points in the interior of the same cone, this will be like lambda 1, lambda 2. These two one-parameter subgroups converge to the same point in the boundary of the toric variety. But if I had some lambda 3 in a different cone, this one would converge to a different point than lambda 1. So using this idea, I can recover the fan. And the same sort of idea works if you're given, one of these varieties satisfying these three conditions, you can recover the hyperplane arrangement in the same way. So here I have V, the additive group. I have my Matroid Schubert variety, sub A. V, so again, I'm going to consider homomorphisms into my group, this time from the additive group, but this is just identified with the vector space itself, right? I'm doing linear maps from the ground field to a vector space. So this is just V. And I'm going to define an equivalence relation where given two vectors, V1 and V2 in here, I say they're equivalent if kind of as you scale them, t times V1 and t times V2, as t goes to infinity, these two limits lie in the same boundary point in the boundary of y this time. And this equivalence relation on the vector space, it cuts out these strata, it cuts out these flats. And kind of if you know all the flats, you know the hyperplane arrangement. So these are my two comparisons. Fans are like hyperplane arrangements are like fans. These flats, these strata are like the cones. And there's a an isomorphism of posets between orbits and flats. And yeah, so this, I think, yeah, so this is all I had to say. So yeah, I'll stop there. Any questions that you have or thoughts that you have?
A small question,
might
please.
be interesting. Yeah.
About the limits coincide. Well, is it true that limits coincide if and only if they lie in the same orbit?
Yeah, that's true. Yeah.
Okay, thank you.
So every orbit has a distinguished point, and all limits, all one variable limits go to the distinguished point. Yeah.
Thank you.
I was wondering, does this construction like have some functoriality? I mean, are there some transformations of matroids that correspond to equivariant maps of those YAs?
Yes, absolutely. So there's two generalizations that I have in my paper that I didn't say for time reasons. So the first, as you mentioned, is morphisms. So a morphism of equivariant compactifications, this makes sense. It's a map of varieties that restricts to a group map. These correspond to some notion of a morphism of hyperplane arrangements. And what that notion is I have two vector spaces and a hyperplane arrangement in each one. And I have a linear map between the vector spaces such that the preimage of a hyperplane is a hyperplane. Or else I also allow that the preimage of a hyperplane is the whole vector space. But the preimage of a hyperplane has to be distinguished. That's the notion of morphism. And there's an equivalence of categories there if you use these morphisms on both sides. And also, you can classify partial compactifications. So these YAs were all compact. But if you remove the compactness hypothesis, you can define what I call a partial hyperplane arrangement. So it's like a hyperplane arrangement, but maybe some of the strata are missing, or in the poset of strata locally you see a hyperplane arrangement, the same way that locally in the fan you see a cone, something like this.
So it's an equivalence of categories, right?
Yeah, that's right.
That's cool. Thank you.
I'll go to my thank you slide. Other questions?
So the Y variety is always projective, no? If I understood correctly.
Yeah, that's right. Yeah, so you only have to assume that it's proper, but it turns out to always be projective.
Yeah, I'm again confused how your hypothesis. I mean, your theorem had three very simple conditions that actually imply many other things.
Yeah.
So that also implies projective, those three conditions in the theorem.
Because
Yeah,
this is closed in the product of P1s, right?
Yeah, in the very first slide. But how do you get that it's projective from these 3 points? I mean,
yeah. So I mean, I can describe in a sentence or two roughly how the proof goes, if you want, but I don't have like a very quick, intuitive, like, yeah, you get projective for free. I don't have a good explanation.
And you also get Cohen-Macaulay for free.
And you get Cohen-Macaulay for free. That's right. Yeah.
And maybe it is good to summarize what do we know about the geometry of such varieties. You explain us somehow this interior structure, but concerning geometry, firstly, projective, singular, normal, Cohen-Macaulay. What else do you know about the geometry?
Yeah, sure. So I know that it in fact has rational singularities. That's one. So I know that, so there are some facts about equivariant completion. So like the fundamental group is trivial. The Picard group is freely generated by the hyperplanes. The class, I mean, as you know, the class group is given by components of the boundary. We know it's a cohomology ring. This was in the work of Ha and Wang. The intersection cohomology is understood combinatorially. That's part of their work. Other things. So we know the singular smooth locus, which orbits lie in there.
And what is a singular locus?
Yeah, so these flats, let me see if I have a picture. So these flats form a poset. So the way you typically write this is the vector space goes at the bottom, and then you go up in codimension. So here's this poset. And so what I do to identify the singular locus is I look at an element in this poset. So for instance, this one, and I look at how many elements cover it. So directly above, I count how many there are, and I compare it to the height from this one to the top. So here, the height from the bottom to the top is 2, but the number of elements that cover the bottom element is 3. And if this is ever different, then it's singular. Yeah, and this is really sort of, so for a toric variety, how do I know if a cone, the orbit corresponding to a cone, lies in the singular locus? I count the number of rays in the cone and see, is it simplicial or not? Okay, so this is the simplicial locus, not the smooth locus, but you know, I think about this as like the statement that a cone is simplicial if it has just dimension many rays in it. Yeah. Yeah, other geometric properties. Yeah, so I know the Hilbert polynomial in P1 to the n. Yeah. Any other ones you had in mind?
Oh, this is already quite a long list. Quite impressive. Okay.
So can I ask you another question?
Yeah, please.
So I think we've only seen one example so far, no? So the product of P1s. The other one was a non-example. Yes?
Yeah.
Yeah. So for some, maybe you know Federico Castillo, he's also from the combinatorics world.
Yeah.
He just happened to be here like 1 month ago when he was interested in this Ivan Arjantsev additive group, so vector group compactifications on this polytopes inside the box. And we just started thinking, randomly about that. And you, Ivan, you had the question when you have finite number of orbits in your paper in PAMS at the end. So we started thinking about that, and we have an idea. We were just playing, but so here comes my question. I think that having finitely many orbits, it's enough to have your other condition. In the case, the example is toric. So the question is, do you have an example that is not toric? So the only example we've seen so far, it's also toric.
So this example, this one isn't toric.
Okay, and it's, oh yeah, I couldn't follow that one.
Yeah. So it's because I blew up 3 points. This won't be a toric blow up.
Yeah, you blew up 3 points in P2. It can still be toric, no?
Oh yeah, that's true. But they're in a line. So if I blow up 3 general points in P2, it'll still be toric. But 3 points in a line.
All 3 were in the same line. Okay.
Yeah.
Okay, so not all of them are toric. Yes, thanks.
Yeah, and in fact, I strongly believe that the only toric one is P1 to the n. I think most of them are just not going to be toric.
Okay.
For this class of variety, to be smooth is equivalent to be toric, right?
Yeah. Yeah.
Possibly.
Yeah.
Dear colleagues, do we have more questions, comments, suggestions?
I have a question.
Sure, you're welcome.
So the question is, are there other, so I know there are these examples that have finitely many orbits, and there are these projective spaces that Hafsid and Schinkel describe, like every projective space can have finitely many orbits under some action. Do you know other examples where there are finitely many orbits?
Sasha, as far as I remember, you thought about these questions, construct examples with finitely many orbits. Can you comment on this?
Yeah. So I asked because we have a guess for what this class should be, and I'm curious if you know any examples that break our conjecture. So the idea was you have P1 to the n, and P1 is an equivariant compactification. But I could take this Hafsid and Schinkel projective space with finitely many orbits, and I could take products of this for projective spaces of various dimensions. And I could take the closure of a subspace in there. And this is one thing that me and Botong and Connor Simpson, my academic brother, we're thinking about this problem right now. And we're writing a paper about this. And we're just sort of interested in the geometry of this example. But we're also very curious, could this be all of the ones that have finitely many orbits? Because it's sort of the join of Matroid Schubert varieties and also these Hassett-Chinkel projective spaces. And these are all the examples that we know of equivariant completions with finitely many orbits.
Okay, so let us think about your question. Looks very natural, but no immediate answer. So we need some time to think about this.
So I didn't really understood the thing. You said that there were probably only products of the Hassett-Chinkel example?
So I want to take products of the Hassett-Chinkel examples. And then in the dense vector group, I choose some subspace and take the closure.
Ah, okay, you chose.
And these will correspond not to hyperplane arrangements, but to linear subspace arrangements, where I don't require codimension 1. And this correspondence is what we're thinking about now. But yeah, it would be cool if there were also some conditions like these conditions that say, you know, if you satisfy these 3 conditions, then you are the closure of a subspace in a product of Hassett-Chinkel projective spaces.
Mm-hmm.
Okay, so this is a question to think about. So, okay, if we have no more questions and comments, then let me thank on behalf of us to Colin for his excellent, very clear, explicit talk. It's nice to have such an introduction to the subject, and we now know what Matroids are, and this is very useful information for us. And this excellent class of varieties, we should study this from point of view of algebraic transformation groups and combinatorics. So very nice. Thank you very much, Colin.
Yes, thank you all. If you have any questions or want, you know, anything, feel free to email me. I'd love to talk more.
Again, concerning your question, I hope we will have email correspondence because it's interesting to think about this.
Very good. All right. Thank you all.
Thank you.
Okay.